All right. I think we're going to make a start. Just, all right, one moment. Okay, I'm going to make a start now. Good afternoon, everyone, and welcome to our first class for this semester. I am a bit of a novice at holding online meetings, so you'll see with me, I'll improve as the semester goes on. Where I have posted, well, certainly one important video on the site, and we can go ahead if you haven't looked at it. I hope it will give some information regarding the course and how we're going to do the labs and so on. And I'd like to, because we have limited time now, I'd like to go straight into this. I must bring up the recording first, all right? All right, I will probably, I'll try and keep an eye on the chat as we go along. So I'm going to start our show now. Right. The first week or two really is a review of discrete signals systems. I'm not sure how much you do in signals and systems regarding discrete time signals and systems. But, I'm sure you won't mind reviewing material. So our main objective of this unit is to be able to understand, get familiar with the mathematical notation, describe and manipulate the discrete time systems. Can everybody mute their mic while this is going on? Right.
Sorry, look like you're going to have to mute everybody.
Right. As I said, I'm a novice. I'm still just trying to come up with it. Yes, I'm remembering to record the class. I'm going to stop it and start recording again. Right. Okay. Gonna start recording again. Our objectives this afternoon then are to be able to understand and apply the mathematical notations that we use in DSP to manipulate discrete time systems and signals. We'll start first by looking at our signals. Right, the rationale regarding DSP is that any discrete time signal may be comprised of samples of a continuous time signal. Whether the samples are a continuous time signal or not, it does not matter. We can still process them. In other words, if the signals come as a discrete time signal, it does not matter. We can still sample a discrete time signal and process it. So if the response of a digital signal to a single sample of unit magnitude is known, we basically say then that we know the impulse response of that system, and therefore we can apply that impulse response to an input signal, and we can determine the outputs. So our discrete time signal will be represented as a sequence of numbers. Here is the first form of notation. Our signal is represented by X. We may just refer to it as X, but it is really a sequence. Our integer n inside the square bracket represents the number of the sample that we are processing. So it may be the first, second, third, and so on. N is always going to be an integer, never anything but an integer. Now, the n sample of a sequence is equal to the value of the analog signal that is being sampled at time t equal nt. We will look at sampling as we go along a bit further. Therefore, we could also write xn is equal to xa, which is the analog signal, and at a particular time period, which is given by n, the index number, and t, the sampling period. We should note that x of n is undefined for non-integer values of n. So it's not as if we have x of n plus 1.5. All right, it's always going to be an integer number inside. And in between those samples, we don't try and define what our signal was. Although x of n is strictly the nth number in a sequence, we often refer to it as the nth sample because we are sampling an analog signal. Okay, so let us get really down to our sequence. Here is a sequence we have written. Our sequence is x. The values are shown here, xn. And we just choose a short sequence, 5, 3, 2, minus 7, 0, minus 4, 8. So in this example above here, our values of n are undefined. We haven't said which one is the the first value, the 0th value, or a negative value of n. So here we will see that an arrow is being inserted, and this arrow is going to show us the 0th value of our sequence. I am sorry, just hold a second. I'm trying to get. All right, so let's continue. All right, so what is the value of our x of 0 in the sequence below? It is 2. So x of 0, sorry, is equal to 2. What does that make the other values in our sequence? At what value of n? We go to the left, we go negative. So this is x of 0, this is x of -1, x of -2. And on the other side, we have x of 1 being -7, x of 2 being 0, and so on. All right, now since x is a time sequence, we are moving then from, on the left, we are moving from the past to the future. Right? So these are values which have come in at the past, and these are future values. We'll see a bit more about past and future values in a little while. All right, so it's important to remember then that our x of 0 represents the sample currently being processed, that values of the sequence for which n is positive are future values and are therefore not real-time processing, yes?
So there are some processes in the waiting room
to get into the and they can't. Okay. All right. While I'm waiting for them to join, I am interested in knowing if Mr. Duplessis is online. I don't see his name. Has anybody been in contact with him?
Yes, sir.
So he knows about the do you think he knows about this class then?
Yes, sir.
Oh, okay.
Yes, sir, he got in.
Oh, he's in now?
Oh, wait.
All right, you'll have a recording to listen to. Right, so values of the sequence for which n is positive are future values and really not available in real-time processing. In other words, we don't know what will be coming in the next minutes or seconds and so on. Again, we're repeating some of what was already said. The values of x for non-integer values are undefined. It's not really that they don't exist, but we don't need to know them right now. Well, we don't need to know them at all, really. And the discrete time sequences that we will be dealing with may be finite length or infinite length sequences. Theoretically, we can we can extend to infinite length sequences, but in practice, as you know, every sequence is going to be of a finite length. Okay. All right. Finally, I'll mention that sequences they are generally going to be real numbers, in other words, not complex. So they will be 5, 2.7, whatever. However, you can have complex sequences, and we will see as we go later on that digital processing of a real sequence can and very often does produce a complex sequence. So we should be well upon our complex numbers, I'm sure that we are. Okay. Discrete time signals then are often depicted graphically, as shown there. These are known as stem plots, and the MATLAB function will plot it for you simply using stem. Again, here I am repeating a bit. Our sequence more than likely will arise from the periodic sampling of a continuous time signal. And here again, we're just reiterating that if our xn is a sample of a continuous time signal xc of t, where little t, being the continuous variable, is equal to nt. In other words, it's sampling a continuous time signal at t seconds periodically, and we are getting our sequence x of n. All right, and I'll leave that, come back to it later. Right, so having said a lot about discrete time signals now, how do we manipulate them? You can add them, so you can sum two sequences, x of n, y of n, and we can also multiply two sequences sample by sample. We can also shift them. Theoretically, we could shift, theoretically we can shift right or left. One is going to delay the signal, the other one is going to advance the signal. We can always delay a signal, but we can't advance it, not in real time. When we're going to shift a signal here, we're actually going to then generate a new sequence, x of n, y of n, sorry, and here is our original sequence, and this NO there is our shifting number, how many samples we're going to shift it by. We'll look at that over here. So here we're given two sequences, A and B, A shown there and B here. So we can add them. Now, adding them is going to give us this sequence here. And you may look and say, but hold on, the first two, the values here are 4 for A and B, 8 for B. Well, we must take into account which is our 0th value. So we cannot, if this is 0, minus 1, minus 2, minus 3, minus 4, we cannot add minus 2, n equal minus 2 to n equal minus 4 value. So the n equal minus 4 value in this sequence here is outside of the bracket. What does that mean? Whatever is outside of the bracket means 0, right? There's a 0 there. So in this case here, we're adding 8 to 0 and getting 0. We're adding 0 to 0 and getting 0. However, we're adding 1 to 4 and getting 5. 1 to 4, minus 2 to 7 is 5, and so on. 1 to minus 1 will give us 0. So this value here, see if it's, no, the arrow is missing from this one here. But you should be aware then that the arrow should go here, that's the typo, and so on. And then for the next set of values, 0 to 3 will give you 3, 0 to 15, another typo, 5 should be there, and so on. Seem to have a lot of typos in this. Anyway, I will correct it, or better still, you can correct it. So this should be the sequence A plus B.
Sir, that's one question. Sorry to cut you.
Right.
You said the arrows, where the arrows are pointed, those are the 0 point, correct?
Yes, those are the 0 points. N equals 0.
Oh, so the numbers that are would be at the left of the arrow will go in a minus order. That's what you're saying.
You're right. This is n equals 0 would be this term here. N equal, we're out of time already. I will shut down and restart in a minute, all right? Let us get this slide finished. So this term here corresponds to this term here. So when we're adding the sequences, we can only add the sequences with the corresponding number of n. So we can add n minus 1s, n zeros, n plus 1s, and so on. So really, this should be, as I said here, n of 0 in our summation would be that term plus that term, which would be that term, and so on. 0 and 3, correct there. Oh, well, yes, minus 10, sorry, and 15 would give 5. Minus 6 and 9 would give 3. So it's not a typo. The only thing missing is our arrow to indicate that term. So as we go along, we'll see that mathematically we're not going to be using this method of indicating our 0th term. We're going to see that mathematically when we write it a different way, we will not be liable to make mistakes like that. All right. For our multiplication then, we're going to be multiplying A times B, and again, the first term in here is for n is equal minus 1, minus 2, minus 3, minus 4. So it is our minus 4th term, right? Here our minus 4th term will be 0, and therefore 8 times 0 going to give us 0. Similarly here, well, 0 times 0 would give us 0, and then 1 times 4 would give us 4. Minus 2 times 7 would give us minus 14, and so on. So have a look for yourself, work it out. Let me know any other typos that have been made. We'll go on to the next slide now. So note that all values outside of brackets for a given sequence are 0. Right. Simpler then. If, for example, our variable y was equal to 3 times a, then, and I'm sure this should be y and not a, so y now is simply going to be 3 times a, which if we look back here, we saw that 3 times 4 is 12, 3 times 7, 21, minus 3. So we expect to see that 12, 21 minus 3, 9, 45, and so on. So this is a straight multiplication. Now, while I'm talking about it, I'll just mention that in MATLAB, you can certainly check everything. I just didn't have time to go and check all my calculations. But in MATLAB, fairly simple. Put in your sequence, do the tell it what to do with it, and it will give you the answer. Say straight 3 times a is just, you would just put it in and get your answer like this. But what about where you wanted to multiply 2 sequences which have different lengths, for example? So in that case now you have to do what is called a dot product in MATLAB. So the best thing is that you look it up in the help file and understand what the dot product is. So the dot product will take a term by term multiplication of your sequence. The straight product here is just going to multiply every term by the same value. Okay, so there you can do the 2 different types of multiplication and addition in MATLAB using what is known as the dot product. So when you go in to do the labs, and I posted the first lab, then you can look up your dot products. All right. We'll do time shifting and then we take a little break here. Right. So a sequence can be delayed or shifted by now doing a calculation where we use a shifting number here, in this case NO, and here is an example to help explain it. So we go back and let's use our original sequence, x of n is equal to this. If we decide to shift our sequence, in other words, apply this equation where NO is equal to 2, then all we're going to do is we're going to get a delayed copy, delayed by 2 time periods of x. So here, this is our x of 0's value, and having delayed it, we've shifted left, and this now becomes our x of 0's value. Now, it does give people a lot of trouble. What do we mean? Why delaying is shifting left? Well, it's always good to remember that if you, supposing you get up this morning and say, well, I was gonna have the car washed today, or I'm gonna wash the car. I was going to wash the car today, but I decided to delay it, and I'm going to do it tomorrow. Well, what you've actually done is that you've actually put that action into the future. All right, so you're then shifting your sequence to the right. In other words, you've move your sequence further into the future. So still your values, your future values are on the right, your past values on the left. So here we had two past values. Now you have no past values. You've shifted everything to the right. So delaying or shifting is just a matter of moving your zeroth value whichever way you intend to. Now, in the case where n naught is negative, then the term inside the bracket becomes n naught plus n, and therefore you're advancing in time. You're not delaying anymore. You're advancing. All right, this is what you would expect to see for advance. Such signals, if you could produce them, are what we call non-causal or anti-causal. Well, anti-causal means that you've moved everything over. Non-causal means that you may still have, you have shifted some signals into the future. You may still have some signals in the past, right? So either of these two terms will be experienced. And as I say, anti-causal signals cannot be realized in real time. Mathematically, we can. Neither can non-causal, because that means you know both what is in the future and what is in the past, right? But we may still consider them mathematically. Okay.
So you can go to the last 10 minutes.
I think I better. All right, less than 1 minute. All right, so let's break here. Let's actually break for about 10
I've only about 6 months reaction than a 6 months.
So me also must say 8 grand for that. Me wonder.
Um, okay, everybody. Tyan who wants to set up and host the meeting. My problem is that I only have about 5 minutes of material left, and then we're going to look at maybe talk about some problems. So I don't know if it really makes sense going over to that room there. He doesn't have the time limit, and yeah, that would be fine if I had a lot of material. But we're almost wrapping up for today because I'm having some issues with the computer. I have to use another computer because my version of Windows doesn't work properly with Zoom. So I borrowed this one and I'm just having a little problem doing certain things on it. I'm gonna let me see, we have 19. I would prefer just to stay with what I have now. All right, simpler question. Has anybody heard from Tyan Hope regarding moving over to his meeting? If so, and you want to go over, well, let's do it.
Sir, them soon join the class and we just tell them not to go. Them probably in the waiting room, so I can let them in.
Yeah, oh, okay, all right. Let me do that. All right, we're going to continue using this one week, and next week we'll set it up so we don't have to be interrupted. However, the 40 minutes kind of suited me okay because I would talk for about 30, we take a break, and we schedule the second half of the meeting for the next, half hour, and do it that way. Anyway, we'll sort that out. We'll sort that out after this meeting here. So what I just want to do is get going again. All right, I have.
Remember to record when you're starting back, please, sir.
All right, right. Yeah. Give me about 2 minutes. I'm having about a little issue with my laptop here, so just give me a few minutes.
All right, sir.
Sir, if you're talking or something, sir, you know your mic mute.
No, man, I don't think he's talking. I'm saying my dude's up.
Okay.
Yeah, I wasn't talking. I was trying to get a few things sorted out here. Okay, I'm going to continue now then. I need to refresh myself on this software. Right, we are going to then look at some basic discrete time signals. Now, the signals that we are looking at, I'm sure you're familiar with them in the continuous time form. In other words, your step function, your delta function, and even your sinusoids. We're going to look at them in our discrete time domain, in discrete form.
Sir, I don't think you're recording.
I'm not recording. All right, come, let me try this thing here. All right, starting now. I'll start over again. So we're going to look at some basic discrete time signals. I'm sure you're familiar with them in the continuous time domain. We will look at how they're represented in the discrete time domain, and we'll see that they actually have a lot more functionality in the discrete time processing. So we'll start then with our unit sample sequence, delta n, the plot of which is shown here, and is defined as being 1 when n equals 0 and 0 at all other times. So system is often referred to as discrete time impulse, or just impulse function, discrete impulse function. It plays the same role for discrete time signals as the Dirac delta function does for continuous time signals. However, as said here, there are no mathematical complications in its definition. In other words, the discrete time delta function is simply, as you see there, it is 1 when equals 0 and 0 at all other times. Is everybody hearing all right? I hope. All right, what do we mean by no mathematical complications? The Dirac delta function in continuous time has infinite amplitude. It has infinite amplitude and 0 width, as far as I remember. You'll probably remember better. We have no such issue in discrete time. We cannot generate a Dirac delta function in continuous time. It's very easy to create your delta function in discrete time. And in discrete time, we can do quite a lot with our impulse function. One of the things that we can do is that we can represent a sequence as a function of unit impulse functions. So here we look again at our sequence here, where 2 is our 0th value, and we can see that it can be written in this form here, where x of n is equal to this equation here, and it will just be better just to go through it. Okay, now this is a sum of impulse functions, right? But they are shifted. So if we look here, we see that the only term in this equation here that has a non-zero value is where for x of 0 would be 2 delta 0 here. That would be the only non-zero term. All these other terms have a non-zero value in them, and therefore these all go to 0. So when n is equal to 0, delta n plus 2 is a delta of 2, and that is 0. So this term will go out, that term will go out. Similarly, all these other terms are 0, and the only non-zero term when n is equal to 0 is 2. Therefore, we have it there. If we choose, for example, n equal minus 2, so here this is the 0th term, the minus 1th term, minus 2th term, right? So here n is equal to minus 2 plus 2 gives you 0. Delta 0 is 1, and therefore x of minus 2 is 5. And so on. I leave you to work it through on your own. And you can do the positive terms. Thus, we have eliminated the need to use an arrow to indicate the term n equals 0. So now we can mathematically write this in a much more elegant way, as shown there. Right, now, so in general then, any sequence can be written as the sum of these terms, right, and our delta function here. So if we were to look back, not good. Right, if we were to look back, then we can see that this is a summation of terms, and written out in length, then we can write it this way. In other words, for here, our limits will not need to be minus infinity or infinity. And these are our terms, the values, sequence values, and this is the delta function. So a good little exercise would be to write out the terms here. So you know that your limits are going to be, you have minus 2, well, from minus 4 to plus 2. So here you would substitute your whatever, minus 4 to plus 2, and that would be all you would write for that expression there, because you know what your sequence is here. Right, your second basic time signal is the unit step sequence, which corresponds to your step function in continuous time, right? And it's defined then as being 1 for n equal or greater than 0, 0 for n less than 0. Again, maybe written in terms of our delta function. Now, I realize that something is wrong here with this expression. So I thought, well, before I correct it, I will tell you that something is wrong with it. And when we finish in a few minutes, I'm going to pause, and I want to see if anybody can come up with what is wrong with this expression here, specifically the right-hand side, because this side here is your signal, your step sequence. Here is how you define it in terms of your delta function. So in a few minutes, we'll come back and I'll ask you to tell me what is wrong with this. Alternatively, we may express our delta function, our step function, as step sequence in this form here. Simply, of course, delta n plus delta n minus 1, delta n minus 2, so on, which goes away to infinity. So this expression is correct, right? It is the sum of terms from k equals 0 to infinity of delta n minus k. and so K equals 0, 1, 2, and so on. So this is correct, but the previous one has an error. Finally, for today, I was going to make this my last slide anyway. Exponential sequences. Important for analyzing and representing discrete time systems. We'll see more about that as we go along. The general form, x of n is equal to a alpha to the power n. Right? If a and alpha. If a and alpha are real numbers, then the sequence is real. If alpha is between 0 and 1 is positive and a is positive, then the sequences are positive and decrease with increasing n like this. So won't say too much about them now. Finally, exponential sequences as shown here. Again, these are in discrete time. Notice that this looks like your sine wave here, or in this case is supposed to be a cosine wave. And here is the expression for our discrete version of the continuous signal. So it's A cos omega n. So t is effectively replaced by a function. This omega is not, in this case, is not, well, normally 2 pi s, yes. But, well, we'll talk about it when we go along further. There is a little adjustment to be done here with the omega n and your phase shift phi for all values of n, with typically a and phi being real constants. And that is where I was going to halt on our sinusoids, because the next part is quite a bit. I thought we might be a bit tired of doing theory for so much. So we will continue with exponential sequences next week. All right, well, as a little exercise for you to spend the rest of the time, not much time left, I will go back and I will ask you if you can find out what is wrong with this part of the expression here. Now, don't know how much you have done with this in signals and systems. So I'm going to just monitor the chat room chats, and I can bring it out. I don't know how to find it again. There it goes. Right. So does anybody not have a clue?
Sir, not a clue. Sir, excuse me, sir.
Eh?
For this, the slides and the PowerPoint, will it be posted on Canvas?
Will it? Yes, in fact, I am supposed to be recording everything and putting it on Canvas.
Yes, sir, but the PowerPoint differently from the recording, sir, I was asking about.
Yes, I will put the PowerPoint just without recording, and I'll put the other one with the video on. I'll put both of them on. What I might do is re-record the video, because I was struggling to do all kinds of things at the same time. So I will probably re-record it. I'm stopping the recording now anyway. So I'm going to re-record it without any break, and we go right through. I'll go right through, and that will be posted. And the PowerPoints will be posted. I
question. You have any recommended text?
Right. All of that is on Canvas, you know. You haven't had a look through Canvas?
I get a look in.
All right. All right. Because we're going to run out. We only have 5 minutes left. Okay. Try and look at this just as we are here now. I can't write, so we know that U of n, our step sequence, is equal to 0 for all values of n less than 0 and 1 for values of n equal or greater than 0. So just simply a matter of plugging in some values. So if, for example, we plugged in n equal -2, just for example, we don't need to go back to minus infinity or anything. -2, even -1. But let's say, for example, n is equal to -1. Now we know that U of n is equal to 0. So putting it into this term here should give us 0, right? So here, this little n up here is -1. And I'm sure, anyway, but I'll try another day. But so -1 from k equal -infinity to -1, right? And this is so k going -infinity right up to -1 is going to this is going to be all 0. And then when you get k equals 0, right, this is going to be delta 0, that is going to be 1, right? Now, when you look at it here now, what is the purpose of n right here? Right? Because n was -2. So, k would be going right up to -2, would be giving us 0 anyway. But it didn't take into account all the other values. Supposing one of the other values gave us a 1 here. So I think that is my contention. But we'll see as we go along, there's something else wrong. All right. So same thing with U of -1. You'd go from k equal -infinity to -1. Then U of 0. So k going from -infinity to what did I say, 0. So when k gets to 0, that is all right, still within that limit. So you get 1, right? So U of n equal 1 now. We know that this term should be 1. So -infinity goes up to 0, and you get 1, and then you go to n equal k equal 1 there, right? Still 0 again. So that is correct there. So let us look now at 2. N equal 2. We know that U of n equal 1. So we go from -infinity to 0. And 0 would give you 1. So U of that would be 1. Yes, you go to k equal +1. Yeah, that is 0. So U of n. So it is correct. But something seemed to be missing here. I guess all they're saying here is that whichever value of n, you wouldn't exceed that and go on to +infinity. You wouldn't need to do the calculations above n. So, yes, it seems that this term expression is all right. I had thought maybe it should be n minus k, but it seems that this is all right. Let me look at what is the next slide here. N minus K. All right, well, good thing is then this term is correct, but I thought it would be an exercise